This is section 14, optimization, example 1. So now we're going to talk about optimization. And when you think optimization, you should think the best, right? That best outcome you could come up with. And really what we're doing is we're maximizing something. We're trying to maximize our profit, or based on how much something costs versus how much material it would take to build. Or what's the biggest area we can come up with? What's the biggest volume we could come up with of something? So when we do this, you know that you're solving an optimization problem when it says largest or biggest or even smallest, right? If that's what you want. Or maximize, right? What gives us the maximum value possible, okay? So to do this, the first thing we're going to do is read the problem and draw a picture, right? Always draw a picture if possible. And you'll see on these problems, all the pictures are already here for you, but when you do problems on your own, you need to draw a figure to give you an idea of what's happening. Then we need to write equations. Okay, one of the equations at least has to have a variable that you're trying to maximize. And so to come up with that, you have to pay attention to what the problem's asking you to do. Then you take the derivative, set it equal to 0, solve for the variable, and then plug it back in to find the original equation, and make sure you answer the question that's being asked. So here's an example. Example 1. A farmer with 4,000 meter of fencing, wants to enclose a rectangular plot that borders a straight river. If the farmer does not fence the side along the river, what is the largest rectangular area that can be enclosed? All right, so it says the largest rectangular area. That's what we're maximizing. That's the optimization. Now, if I find the area of a rectangle, I know it's just base times height, or length times width. In this case, if you look at the letters here, we have x and y, which means that area is just x times y. Now, they give us some information. They tell us that we have 4,000 meters of fencing. Okay, and to find the amount of fencing we would use, we would just add up all the sides. So 4,000 is going to equal all the sides added together. There are two x's, so 2x plus y. Now when we do this, when we do optimization problems, if you end up with two equations, which will happen, you really need to bring it down to 1. And we need that one equation to have our maximum, to have the variable that we're trying to maximize in it. Okay, so you don't want, in this case, the a equals xy to go into the red equation. That doesn't make sense, right? It's already solved for a. That's going to be the ideal situation to take the red equation and plug it into the purple equation. So let's go ahead and solve for a variable. It doesn't matter which one you solve for. Just pick one. All right, I think y is easier to solve for because you just subtract 2x. So y is going to equal 4,000 minus 2x. And now I'm going to take this and plug it in right here. Right, direct substitution. So a is going to equal x times 4,000 minus 2x. And this is what I'm optimizing. Now there's two ways you can do this. You are going to have to take the derivative. So we can either leave it like this and use the product rule, or we can distribute things out and just use the power rule, which is much faster and easier. So a actually equals 4,000 x minus 2x squared. I need to find a prime. So we get 4,000 minus 4x, and that's what's going to equal 0. So remember, to maximize something, to find a maximum value, you would use what we did in function analysis. You'd take the derivative, set it equal to 0, and find that particular x value. So that's all we're going to do. That's the whole idea. So let's go ahead and do that. That means negative 4x equals negative 4,000, which means x equals 1,000. Now remember, our job is to answer the question. It says, what is the largest rectangular area? All right, so to find the area, we would need the x and the y to plug it into a. So the y is going to equal 4,000 minus 2 times 1,000, which means y is 2,000. So the maximum area is x times y, So 1,000 times 2,000, which is 6 zeros. So 2 million, and what's the unit? Meters squared. So 2 million square meters. That's the largest rectangular area that can be enclosed.